So proposition U V bounded open sets in Rn T U to V Diffeo E contained in U Lebesgue measurable, then TE is Lebesgue measurable in V. So this is now, converse is obviously true, you apply it to T inverse. So if something is Lebesgue measurable in V, then its inverse image will be Lebesgue measurable in U. So we did it for Borel sets, we knew. So now we are proving it for Lebesgue measurable sets. Okay. Now E Lebesgue measurable in Rn. So what do you mean by this? Then there exists A F sigma, B G delta, such that A is contained in E is contained in B, and Mn of B minus E is 0, Mn of E minus A is 0. This we have seen from the characterization of Lebesgue measurable sets. And therefore, you can write E as A union E minus A. Okay, and this A is of course a Borel set, and E minus A is contained in B minus A, which is Borel, and Mn of B minus A equal to 0. Okay. Now conversely, if you have E equals A union G, where A Borel and G contained in H Borel and Mn of H 0. Then A is of course Borel, so Lebesgue Borel implies Lebesgue measurable. And G is a subset of a set of measures 0, and therefore this is Lebesgue measurable by completeness. Therefore E is Lebesgue measurable. So another characterization of Lebesgue measurable set. So E Lebesgue measurable if and only if E equals F union N, F Borel, N contained in A Borel, Mn of A is 0. So it is just a Borel set plus a subset of a set of measure 0. Then these are all Lebesgue measurable sets. So now, so you write E in this fashion, then T of F, T of E equals T of F union T of N. Now TA is Borel, and we have already seen that Mn of TA is 0. That corollary we have already proved, because A has measure 0 and Tn is of course contained in T of A. Okay, so Te and Tf is Borel. So this Te is the union of a Borel set and a subset of measure 0. So this implies Te measurable, Lebesgue measurable. So finally we have this following theorem. This is called the change of variable. U V bounded open sets in Rn, T U to V Diffeo, F V to R integrable. So we are not saying it's a Borel measurable function, it's now an integrable function. Then integral v f dmn equals integral of u f composed with t mod jt dmn. Proof. So E contained in U, Lebesgue measurable. Then we write E equals F union N as above. So F is Borel and this is N is a subset of a Borel set of measure 0. Okay, as above, and without loss of generality, you can assume F intersection N is empty. So Mn of T equals Mn of Tf, because Tfn is of measure 0 and therefore, and T is a diffeomorphism, they are disjoint, etc., and therefore this is Mn of Tf. That's equal to integral over F, we have already seen, because it's a Borel set, mod Jt dmn. But I can write this as integral F union N mod Jt dmn, since Mn of N is 0. Okay, sorry about the confusion about N. This is, okay, maybe I should change. M so M, okay, so F union M as before, F intersection M equal to 0, sorry about that, and F union M, okay, Mn of M equal to 0. Which is equal to integral of over E of mod Jt dmn. So dagger holds for, so T G equals T of E. So holds for all chi G equal to F, G Lebesgue measurable. Implies holds for non-negative simple functions, implies holds for non-negative Lebesgue measurable functions, non-negative integrable functions, and then F integrable, you write F equals F plus minus F minus, and dagger holds for F plus minus implies holds for F. So that gives you the change of variable formula for this. So let us see a couple of examples. So first example is something which we do in college. Okay, so F from minus 1, 1 to R. Okay, so we change the variable y equals minus x. Okay, then the interval remains the same. Okay, now how would you do in college? So college method. So you write dy equals minus dx, and therefore you write integral minus 1 to 1 f of x dx is equal to integral f of minus y dx is equal to minus dy, and then minus 1 goes to plus 1 and plus 1 goes to minus 1, and then we say that this is equal to integral minus 1 to 1 of f of minus y dy. Okay, so this is how we would do it. But the correct method, correct interpretation, so t of x equals minus x equal to y. Okay, so mod jt is identically 1. Okay, so because the derivative in this case there's only one function, so t dash is minus 1 and modulus is equal to 1, and therefore integral from and t of minus 1 1 is the same as minus 1 1. Okay, so minus 1 1 of integral of f dm1 is equal to integral equals integral minus 1 1 of f of minus y dm1y. Okay, okay, so this is how we write it, and so this is the correct way of interpreting this thing. So the Jacobian is plus 1, and that's why. So this thing, these are all ad hoc rules where you change the limits of the integral to with a minus sign and so on. Okay. Example, these are about the polar coordinates. So D in R2, open disk, center 0, radius say A positive. So D is equal to set of all xy in R2 such that mod x square plus mod y square is strictly less than A. Now you take V equal to D minus set of all x 0, 0 less or equal to x strictly less than A. So you are taking the disk here and you are removing this radius here, and that is the remaining set V. And U equals 0a cross 0 2 pi, also contained in R2. Then T from U to V, so T of R theta is R xy, where x equals R cos theta, y equals R sin theta. So this is a diffeomorphism between the two sets, and then you have Jt is the determinant of cos theta and then sin theta, then minus R sin theta and R cos theta. And that gives you R. So if f from V to R integrable, you have integral over V f dm2 is equal to integral over U of R f R cos theta R sin theta dm2 r theta. Okay. Now d and v differ by a set of measure 0, and therefore the integral over d f dm2 is also equal to integral over u r f of r cos theta r sin theta dm2 r theta. Okay. So now if f from r2 to r is a non-negative function, then monotone convergence theorem implies, so this d, you can expand this d, so integral over r2 f dm2 is equal to integral over r2 0 infinity cross 0 2 pi of r f of r cos theta r sin theta dm2 r theta. So in particular f greater than or equal to 0 and continuous, then you have integral over r2 f dm2 can be written in terms of the Riemann integral, integral 0 to infinity, integral 0 to 2 pi f of r theta r cos theta r sin theta r dr d theta. This is the familiar change of variable formula which you know, and that comes precisely because the Jacobian has that thing. And then if you have an integrable function, you apply it to f plus and f minus, and you do. So this is about the change of variable. Similarly, you can try your hand at writing down the expression for the, you will see that you will get, when you write polar coordinates in 3 dimensions, cylindrical or spherical, you will get precisely whatever you have been doing in your calculus courses, because the Jacobian will be exactly what you have there. So that is why there is no mystery as to why you get these numbers r dr d theta. Why do you write that? There is no mystery. It's because of the Jacobian. So with this I conclude this course. I hope you enjoyed it, and I hope it was a good learning experience for you. Thank you very much.